Okay guys, so for those of you who keep track of exactly which unit in the book we're covering next, this is over 3.2. We're going to talk a little bit more about MVT. We've already done mean value theorem last unit a little bit, and then we're going to specifically talk about a specific instance in MVT called Rolle's theorem, hence the lovely, ha ha ha, get it. I could never, I just can't pass that up for a good pun. Okay, so real quick reminder, MVT or mean value theorem, if a function f is both continuous on a to b and differentiable on the open interval a to b, then there is at least one number c in ab such that f prime of c is equal to f of b minus f of a over b minus a. Okay, basically the slope at a specific point, or the instantaneous rate of change, is equal to the slope over 2 points, or the average rate of change. Okay. The reason why I brought MVT up again today is another useful version of this is to kind of rearrange it. Okay. So the first thing I'm going to do is I'm going to think this is a single number. Like once I figure out what B and A are, I subtract them and I come up with a single number. I'm going to rearrange this by multiplying B minus A to both sides. So I'm going to end up with f prime of C times B minus A is equal to f of B minus f of A. So far, have I done anything super weird and crazy? No, I just multiply my denominator to both sides. Okay, and you're like, Murphin, why? I don't see where you're going. Just bear with me here for a second. Okay. So then, just because I feel like it, again, because I can, I'm gonna flip sides here and make this f of b minus f of a equals f prime of c times b minus a. Again, I hear you. Why? Why are you doing this? Just wait. Hold on. It'll get there. I promise. Okay? So now I want you to take just a tiny, tiny step back to Algebra 1 for a second. Okay? Your, I don't know, second favorite math class, least favorite math class. It's, one of your math classes that you either enjoyed or hated. I don't know. We use f of b and f of a, but really those represent two different y values, correct? I'm going to call f of b y2, so that means I'm going to call f of a y1 is equal to, I'm going to go back over here. Well, if y2 went with f of b and y1 went with f of a, that means b must have been x2 minus a, which was x1. Okay, so now we have this little guy right here. I can't just not, I have to have something to put here. So we said earlier this represented the slope at a specific point. Well, what's our little symbol for slope from back in our Algebra 1 days? Ah, m is what we used. Okay, and then what I want to do is, oh wait, m, usually when I have m is equal to y2 minus y1 over x2 minus x1. Oh, that means this is in the wrong spot. I need to divide that over. So m, or slope, is equal to y2 minus y1 x2 minus x1. Oh my gosh. MVT, instantaneous rate of change. Slope. Is anybody else shocked by this? No? All right. Well, if you were, great. If not, great. I wanted to show it to you anyway. It's there. Moving on. All right. So given the function f of x is equal to 3 minus 5 over x from 1 to 5, the graph of f of x is shown on the right. Visually, what is the MVT, or the mean value theorem, trying to find? Draw it in. So again, this is one of those opportunities where you can pause the video, attempt it on your own, come back, see if you got the same thing I got. Okay, so MVT is typically trying to find the average rate of change comparing to the instantaneous rate of change. So if I know the average rate of change from 1 to 5, as long as my function is continuous on the closed interval from 1 to 5, but differentiable on the open interval from 1 to 5, there's bound to be a point somewhere between 1 and 5 that the derivative at that value is equal to the overall slope between 1 and 5. So visually the slope of the tangent line at some c in 1, 5 equal to the slope of the secant line between 1 and 5. So if I were to graph this, so f of 1 is here, f of 5, so 1, 2, 3, 4, 5 here, okay? That means if I were to draw the line between these 2 points, let's see if I can get fancy here, like that, okay, there's as long as my function is differentiable and continuous from here to here, there's bound to be some point that the instantaneous rate of change is equal to this average rate of change. And what do you, I feel like it's probably about right there. It's not perfect. Yeah, there we go. Okay. So then part B, show that the mean value theorem applies and find the C that the theorem guarantees. Well, we can tell visually from the graph that on 1 to 5, f of x is continuous. Now, over the entire real line, this function would not be continuous because you can't have 0 in the denominator. However, because they're specifying that we just want to look at 1 to 5, the function is continuous on the interval that we're looking at. So it is continuous on 1 to 5. Okay, so the first step is always make sure your function is continuous on the closed interval a to b. And is it differentiable on the open interval from a to b? Well, let's check. So if I take the derivative, if f of x was equal to, I'm going to go ahead and just write this as 3 minus 5x to the negative 1, f prime of x is equal to 5x to the negative 2, bringing the negative 1 up front, blah, 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 blah. Yeah, I can take the derivative, and so far the only place where this derivative would not exist would be at 0. Again, that's not within the interval, so we are good here. It's still differentiable on 1, 5. If I had any other, not any other interval, but if I had an interval that encompassed x equals 0, I would have a problem. But because 0 is not in the interval that we're looking at, we are good to go. So it's continuous on the closed interval, continuous on the closed interval, differentiable on the open interval. MVT can apply. Okay, so then I need to find the slope of my secant line. So the slope of my secant line is going to be f of 5 minus f of 1 over 5 minus 1. So that's going to be f of 5 is 3 minus 5 over 5. So 3 minus 1, so 2 minus f of 1, 3 minus 5 over 1, so negative 2, over 5 minus 1 is 4. So 2 minus, so 4 over 4. So I have a slope of 1. So I need to find the value where my derivative has a slope or a derivative value is equal to 1. So we already found the derivative a second ago. We wrote that as 5x to the negative 2. I need to set that equal to positive 1. So 1 equals 5 over x squared. Cross multiply x squared is equal to 5. Square root both sides, so x is equal to plus and minus root 5. Technically, that's the solution to this equation. However, because I only want the interval from 1 to 5, I only keep positive root 5. Okay? And if you wanted to specify why negative root 5 is not in 1, 5. It's not in the interval, okay? But whenever you're working these, you need to specify that you get both solutions, but then you also specify or show that you're only going to keep one of them, okay? Because technically the solution to this equation, that's two answers, but for the problem at hand, we only want to keep this one, okay? So then because MVT applies and let's see, show that the mean value theorem applies, check, find the value of C that the theorem guarantees. So this is the value of C that the MVT guarantees, okay? So MVT, essentially, MVT guarantees that f prime at positive root 5 is equal to f of 5 minus f of 1 over 5 minus 1. Okay, this extra part isn't necessarily required, but basically by finding this, this is what you're guaranteeing. That if you found the derivative at root 5, that's equal to the slope between the points f of 1 and f of 5. Okay, so that's a quick recap of MVT. Let's talk specifically about a specific case of MVT called Rolle's theorem. Okay, if a function f is continuous on a closed interval, a to b, differentiable on the open interval from a to b, and the unique situation where f of a is equal to f of b, then there is at least one number c such that, okay, MVT is the same, so you still have f prime of c, f prime of c is equal to f of b minus f of a over b minus a, but we have this added situation where f of a is equal to f of b, so that means f prime of c is equal to, well, if these two things are equal, you're going to get 0 up top, because f of a minus f of b, when a and b are equal, that means they're equal to 0 when you subtract them. Okay, so f prime of c is equal to 0 because f of b equals f of a. Okay, so that means overall what this means, there must be a point somewhere on a to b that has a horizontal tangent. How do I know that? How do I know it has to have a horizontal tangent? It just talks about f prime of c is equal to 0. Ah, f prime of c is equal to 0. This means that your slope is equal to 0, which means you have a horizontal tangent. Okay, so MVT applies in general to any slope. Okay, doesn't matter what it is. Rolle's theorem is only the specific case when that slope is equal to 0. And in that instance, you essentially have, there's got to be a point somewhere between a and b that you have a horizontal tangent, okay, which could be a relative min, could be a relative max, or it could be neither. It could be one of those situations where the graph keeps increasing or decreasing, even though it maybe like slows down at that point, okay? But either way, you know that if f of b is equal to f of a, you have a slope of 0 or horizontal tangent. Okay, let's look at an example. Show that the conditions of Rolle's theorem are met and find the value of c that the Rolle's theorem guarantees. Okay, so the first condition, is this function continuous on -2 to 3? Well, this is a quadratic function. We know that all quadratic functions are continuous, so we're good there. Step 2, is this differentiable on the open interval, -2 to 3? Well, if I take the derivative of a quadratic, the derivative of a quadratic is linear. All linear functions are also continuous over the entire line. So yeah, we're good to go there. Okay. Step 3, or condition number 3, is f of -2 equal to f of 3? Well, I don't know. Let's check. So f of -2 is going to be -2 squared minus -2 minus 6. That's a parentheses. So 4 plus 4 minus 6, I get -2. No, I don't. Haha, that's not a 4. Boop, boop, boop. Boop, boop, boop. Let's just reset. My bad. 4 plus 2 minus 6. That is 0. And then, let's see, what is f of 3? F of 3 is equal to 3 squared minus 3 minus 6. So 9 minus 3 minus 6. Well, 9 minus 3 is 6 minus 6. I get 0. So yes, this condition is also guaranteed. Okay, or it's also met. So now show the conditions of Rolle's theorem are met. Done. Did that. Find the value of C that Rolle's theorem guarantees. Okay, so basically f prime of C is equal to 0 is what we're trying to find out. What is this value right here? Well, let's find out what is f prime of x. F prime of x is going to be 2x minus 1. So then I set that equal to 0. 2x minus 1, bring over the 1, x equals 1/2. So that means if I were to take the derivative, okay, or take the derivative of my function, at 1/2 my derivative is equal to 0, which makes sense. Here's my derivative. If I plug in 1/2 right here, I'm going to get a 0. Okay, so Rolle's theorem guarantees a horizontal tangent at x equals 1/2. Okay? All right, let's try another one. This is another perfect opportunity where you pause the video, try it on your own, come back, see if we get the same thing. All right, welcome back, assuming you paused it. Let f of x equals x to the fourth minus 2x squared. Find all the values of c in the interval from -2 to 2 such that f prime of c is equal to 0. Again, they're not specifying, hey, use Rolle's theorem, but whenever you see this right here, Rolle's theorem, okay? But in order to use that, you need to make sure you check the conditions. So step 1, is this continuous on -2 to 2? This is a polynomial function to the 4th power. All polynomials are always continuous, so we're good there. 2, is this differentiable on, nope, I keep forgetting that, on -2 to 2? Well, the derivative of a quadratic, not a quadratic, a quartic function is a cubic function, and all cubic is another polynomial, so yep, good to go there. Step 3 is f of -2 equal to f of 2. Don't know, so let's say f of -2 is -2 to the 4th minus 2 times -2 squared. Okay, that's going to be 16 minus 8, so I get 8. F of 2 is going to be 2 to the 4th minus 2 times 2 squared. Oh, this is a nice, lovely, even function, because whether you plug in a positive or negative x value, you get the same overall y value, so that's also 8. So that condition is also met. So then I want to find the where f prime of c is equal to 0. So f prime of x is going to be 4x cubed minus 4x. Set that equal to 0. So I'm going to go ahead and factor out 4x, and I'm left with x squared minus 1. Okay, so then 0, well, that means x is equal to 0, 1, and -1. Because remember, this is going to factor, okay, x minus 1, x plus 1. You can't forget that, guys. That's always a thing. Okay, so find all the values of c. All right, these are all the values of c such that f prime of x is equal to, or f prime of c is equal to 0. So Rolle's theorem guarantees horizontal tangents at x equals 0, 1, and -1. Okay? All right, hopefully that makes sense. Now let's talk real world situation here. You are driving a car traveling on an interstate highway at 50 miles per hour, and you pass a police car. Hope you weren't speeding. 4 minutes later, you pass a second police car, and you are again traveling 50 miles per hour. The speed limit on the interstate is 60 miles per hour. Oh, so you're safe. The distance between the two police cars is 5 miles. The patrolman in the second police car gives you a speeding ticket for driving 75 miles per hour. How can he prove that you were speeding? You were going 50 at the time. Let's think about this. How can he prove that you were speeding? Well, you drove a total between the two police cars. You drove a total of 5 miles, and it took you 4 minutes. Okay, so 5 miles in 4 minutes. I need to compare this to miles per hour, so I'm going to go ahead and multiply this by 60 minutes and 1 hour. So that way I'm going to end up with miles per hour. Okay, so if I simplify this math here, 115, 75 miles per hour. So driving 5 miles in 4 minutes equates to 75 miles per hour. Ooh, he can prove that you were speeding pretty easily. Okay, this is kind of an application of the mean value theorem, because the average distance that you drove, or on average, you drove 5 miles over 4 minutes from start to finish. Okay, so then you had to have driven at some point, like on average you drove 75 miles per hour. Well, your speed is continuous. Like there's not a way for you to speed up and then slow back down like instantaneously and jump over numbers. Like you can't start out at 50, drive 90, and then instantly drive 50 later. At some point you have to come back through 75 miles per hour. So yeah, you could basically get a ticket for this. And this is something that typically happens mostly on toll roads. I don't know that it would really happen elsewhere, but a lot of times on a toll booth, because they keep track of what time you enter a toll booth and what time you end the toll booth, you leave the toll on the other end. If you go between if you get from point A to point B a little faster than you're supposed to, you technically could get a ticket. I don't think they do that in Texas, but they do in other states. So just be aware of that. It's a rule, guys. So you foolishly argue with the patrolman who is writing you a speeding ticket, and he calls his brother who is currently taking calculus and has just learned the mean value theorem. Bad news. Now the patrolman writes your ticket and charges you for driving 65 miles per hour twice during the 4 minutes. How can he prove that? So he used the mean value theorem earlier, but then now how does he prove that you drove 65 miles per hour twice? Well, let's think about your speed. You started out when you first entered at 50 miles per hour. At some point, your speed was 75 miles per hour. At least, you know that has to be true, because on average, your average distance traveled was 75 miles per hour. And then you ended again at 50 miles per hour. So if you're just looking at your function of speed in the most basic sense, and you went from 50 to 75 back to 50, well, using what theorem did you have to go through 65 miles per hour? Can anybody tell me what theorem that would be? Anyone? Oh, wait, there's nobody here. Oh, we're on a video. IVT, the intermediate value theorem. Because your speed is continuous, and you know that you went 50 at the beginning and you're going 50 at the end, but he just proved you using mean value theorem that you were going at least 75 at some point. You were actually probably going a lot faster than that, but you know what? Semantics. We're not going to go into that. But because you foolishly argued with the guy, he'd be like, you know what? Hey, you were going 75, but instead I'm going to write you 2 tickets for going 65 miles per hour twice, because if you were going 50 at some point on the beginning and the end and 75 somewhere in the middle, you had to have gone through 65 at least 2 times. Ugh! Math in the real world right there. So basically, guys, the moral of the story is don't argue with the patrolmen. They're going to not be nice. Or at least, find your faults and, write you a ticket for them. So yeah, that is MVT and roles. If you have more questions, this is 3.2 in your textbook. Again, always go back to Khan Academy or Prof. Rob Bob if you have more. Have a good one.